Okay. I have your exams. I have to post the answer key, which I'll do today, and then I'll release the grades, and it'll give you your percentage of where you're at. So it appears as though some of the grade lines in Canvas right now that are set a little bit lower than what they were in the syllabus, because that's where they ended up at the end of last year. So when I copy the Canvas site over, it copies those adjusted lines. So if I switch them back to what's in the syllabus, it'll affect people's grades and freak them out, so I'm not going to do that. But realize that those were probably close to the final grade. So if you're like, I'm doing a little better than what it says, yes, because the lines are a little bit lower. But, and you can come and see me if you're super concerned. If you're going to make any decisions for tomorrow, probably come and see me, or at least email me. Okay. Finishing up chapter 22. And then the chapter 22 problems will be due next Monday. There's a couple things that we just need to review. Now, realize that the first half of chapter 22 is really review on how to make aldehydes and ketones. So I didn't really go over that, and maybe I'll set up a problem assignment, but otherwise that's kind of your review, is to go through those problems. The last couple topics were, it said how to reduce a ketone to an alkane. And so that's kind of a review reaction where we have this ketone, and I'd like to reduce it down to now you can. So it just wasn't set over. So reaction like this. So then I would say, okay, what two reactions do we know that we can do this with? And you would say,
platinum and H2?
No, not platinum and H2. You could do this, I mean, there's three ways, I guess. You could do this with H2. Nope, you can't do it anyway. You can't do it either way. So there's just two ways. Platinum's out. So we have Wolff-Kishner or what goes with Wolff-Kishner? Clemenson. And we remember those reagents? There is no maybe. N2H4, KOH, and heat for Clemenson, zinc, mercury, HCl, and heat. So we still need to remember those because those are methods or the reactions of a ketone to make an alkane. They're probably fairly general so that you could do it without the benzene ring there, but this is where we do most of those reactions. So it's possible. Now, since you brought up the issue of using H2, what happens when I react a ketone with H2 and palladium? Nothing. Right? This is no reaction. Because the palladium isn't a strong enough catalyst. Now, I could do H2 and Raney nickel, And what would that give me? I'm adding 2 hydrogens across the carbon-oxygen double bond. So what functional group am I going to make? And alcohol. Not an alkane. So that's why there's a difference between these. And you could get from the alcohol to an alkane, but it would take at least 2 more steps. Okay. So that's one of the things that they talk about, but we've already done that, so it's review. And the last topic that's in there is what's called conjugate addition. And this one's kind of foreshadowing what we're going to talk about later on. So, first of all, conjugate addition is going to show the difference between Grignards and lithium cuprates and how they react. And I'm going to classify a Grignard as kind of what I would call a hard reagent or a strong reagent as far as the C- goes. But when you make a cuprate is a little bit milder. And I got to put these in quotes because I'm using these to kind of describe so that it kind of can help you hopefully put when one reacts and how one reacts and when the other one doesn't react. And this includes in the future, there's always going to be Grignard is always going to basically be a stronger reagent than a lithium cuprate. So in this case, what we're talking about is we're talking about doing this reaction with what's called an alpha beta unsaturated ketone. So the first thing is that alpha beta terminology is different with carbonyls than it is when we talked about alpha and beta carbons before. Because when we talked about alpha beta carbons before, the alpha carbon was attached to the leaving group, the beta carbon was next to it. In carbonyls, we always letter the carbon next to the carbonyl as alpha and beta, so the carbonyl doesn't get a letter associated with it. So there's 2 possible reactions that can occur here. The first reaction is to take a Grignard, and what the Grignard will do is the Grignard will come in and attack the carbonyl. Okay. And anytime that reaction occurs where it attacks the carbonyl and not what I'll show you in a moment, that's what I consider the reagent to be hard. It's going to be more reactive. And so in this case, what I would end up doing is reducing the carbonyl down to an alcohol. Okay, so Grignards always attack carbonyls. But the lithium cuprate is a little bit milder, and it'll do what's called conjugate addition. So the conjugate addition is the R- on the lithium cuprate will come in and add to the beta carbon. This pair of electrons will move, and the carbon-oxygen double bond pair of electrons will move up to the O. Now, you could think of this, I'm going to number it this way, 1, 2, 3, and 4. You can kind of think of this as 1,4 addition. And so the product of this is going to be an O-, a double bond there, and then the R group will have added to, again, the beta carbon. And then when we add H plus to this, we're going to go ahead and protonate that. Just like up here, we would have protonated the Grignard to give us the final OH product. Over here, we're going to get that molecule, which is an what? That's an enol. Are enol stable? No, so what's going to happen? What? It's going to tautomerize to the ketone. So the pair of electrons between the O and the H are going to go here. This is going to be used to bond the hydrogen. It'll sound like death, but I'll survive. So wasn't the best week to have this, but I'll survive. So we make this ketone. So in the end, what happens is that the R group added to the beta carbon, and then the double bond just disappeared. So this is what's called conjugate addition. And that's the mechanism. That's only if it's an alpha-beta unsaturated ketone or aldehyde. That's only with the lithium cuprate. So the lithium cuprate is kind of a milder reagent that will attack the carbon of the double bond versus the harsher reagent adds to the carbon of the carbonyl. And we're going to see these differences in Grignards and the differences in lithium cuprates later on. In those cases, it's going to be that the Grignard adds like 2 equivalents and the lithium cuprate only adds 1. So that's why I'm kind of classifying this as hard versus moderate or mild, simply because we're going to use this over and over again. Okay, so that was conjugate addition, and they had that as a reaction of a ketone. I think, again, they're foreshadowing what we'll talk about in the remaining carbonyl chapters. All right, so that was all except the review stuff for chapter 22. So today, if we finish chapter 22 today, normally the problems would be due on Friday. They'll be due on Monday for the top hat problems. Okay. All right, so then we move to the next functional group, which is not a carbonyl functional group. It's an amine functional group. And so we need to talk about amines, how to make them, how to react them, some of their physical properties. And the biggest physical property of an amine is its basicity. Because what we know from like general chem is that if you take an amine and you react it with water, it does not lose a proton. It gains a proton from water to form an ammonium and forms a hydroxide. So it is a base. And so we need to lay out the rules and the trends for the basicity of amines. So here's the general big rule. The big rule is anytime you increase the electron density of the nitrogen of an amine, you increase its basicity. So that's the overriding factor. So let's start with something relatively recent. Relatively recent would be, this is aniline, and that's ethylamine. So my question would be, which one of those two is the stronger base? So everybody got cards? If not, I have extra cards. So my question is, which one is more basic? The nitrogen on the ring or the nitrogen on the ethyl group? Okay. Does everybody have cards, or do you need one? You know how to use this?
Yeah.
I have to ask. Okay. And remember, your hand can't cover the square. It doesn't work that way. Okay. 13 to 7A. That A is more basic. Why are you shaking your head?
Because NH2 is an activating group, so it's going to donate electrons to the ring, so the N has less.
That's an interesting thought. So if nitrogen is an electron donating group, it would be pushing electron density into the ring, which would be taking it away from the nitrogen, so that nitrogen would be less basic. And that's exactly what happens. So we have to think about the role of the ring, and while we may initially say, look at the ring and go, well, that will increase the electron density, it really won't, because the nitrogen is going to donate its electron density. That's why it's an activating group. That's why it's an electron donating group. So B is the stronger base simply because it doesn't do that. That nitrogen doesn't do that. As a matter of fact, when you have a carbon, when you have an alkyl group attached to a nitrogen, what does that alkyl group do? It pushes, because the hydrogen of the alkyl group is delta plus, and the carbon is then delta minus, and so it has electron density to inductively push electron density into nitrogen. Okay, that's question number one. So then, again, rule, increase nitrogen's electron density, increase its basicity. What type of group should I add to this benzene ring to make nitrogen more basic. And let me give you some specific groups. A nitro group or a CH3O group. Which of those two groups should I add to the benzene ring in order to make it more basic? What do you think? Do we have an answer? Okay. If nothing else, you can guess. Right. When we get to the final exam, it's all multiple choice, so you could always guess. I think we want to limit our guessing, but whose didn't I get? Nine NO2s and 11 CH3Os. So, discuss for a minute, and then we'll revote.
So splitting up the gel.
Okay, your time is up. So let's revote. Josh, your hand's over the thing. It was. Here's my missing again. Okay. 15 B's and 4. 15 B's and 4 A's. Although it told me it only 17 cards. Anyway, you chose B. Why'd you choose B? Somebody who chose B. That's 15 of you, because only 4 of you chose Kevin.
So our thinking was that the CH3O, when it would attach, it would be putting amines back into the ring, which would essentially give the NH2 more E minus.
Okay, so CH3O is what kind of group? It's an electron donating group because what kind of group is it when it comes to electrophilic aromatic substitution? It's activating, and so this is the activating. What about NO2?
Yeah.
It's a deactivating, which means it pulls electron density out of the ring, which will then pull electron density out of the nitrogen. So this would be a stronger base than NO2. Okay. So again, this is going back to what we just talked about. Well, what we talked about before aldehydes and ketones in terms of electrophilic aromatic substitution. Okay, so that's the basics of basicity, except there is one other thing, and that's, let's say we don't use aromatics. So if I'm going to use a primary amine versus a secondary amine versus a tertiary amine, which one of those would you say is the most basic? Is it the primary amine? Is it the secondary amine? Or is it the tertiary amine? So which one of those do you think is the most basic? A, B, or C? Ready? Eight A's, 3 B's, 8 C's. So it's between this one and this one. What does each alkyl group do? Push or pull? Push. Like this. So each alkyl group pushes electron density into the ring. Into the nitrogen. And so the more alkyl groups, the more pushing of electron density. That's a good thing for basicity. And so the tertiary should be the most basic. However, the real trend is this. It is that an NH3 is the least basic, a primary is approximately the same as a tertiary, and it turns out the secondaries are the most basic. And the reason for this is because it's not just about pushing electron density. We also have to think about the solvation of the amine, because these are all measurements that are made in water. So, depending on the solvation effect, you can end up with, if you end up with a greater solvation of the amine or a greater solvation effect of the ammonium salt, that can push or pull the equilibrium either way. And so that factor comes into play, and what it does is it basically, secondaries are the best in terms of inductive and solvation, in terms of pushing the equilibrium all the way to the right. And your book has a much more detailed explanation of that I'll leave to you to do it, because otherwise I'm just going to get it backwards. But it's a combination of solvation as well as the inductive effects. Okay. So basicity then is something that amines have different basicities, but that overall rule, except in this case, is that the more you push electron density into the nitrogen, the more basic it is. And here, the thing is, solvation comes into effect. Okay. So that's that. Well, I could take a shot at it. Let me take a shot at it. So when you got a tertiary amine, the tertiary ammonium is not going to be well solvated because the plus charge is on the inside of this big smear of alkyl groups. So if that's not well solvated, the equilibrium doesn't get pushed all the way to the right. Now you might say, but what about the primary one? Well, in the case of the primary one, well, that would be enough. The lack of solvation of the tertiary would be enough to move it down a notch so that it's equal to primary. The problem with the primary system is, so what's better solvated? The amine or the ammonium? And so we have to take that into account. But because the tertiary is sterically hindered in its plus charge, it's not solvated as well. And so that equilibrium doesn't get pushed to its maximum, pushing to the right. Okay. So that's why it levels out the tertiary. And the secondary is gaining both induction and solvation, and so now it moves to the front of the line. Okay, so reactions to make amines. How do we make an amine? SN2. Let's say I take something like ethyl chloride, I react it with ammonia, the ammonia comes in, kicks off the chlorine, and I end up making an ammonium, and then the chloride hangs out as a counterion. The interesting thing about amines is when you try and synthesize them, you will always make, by SN2 reactions, you're always going to make the ammonium. Because there's nothing to take away the H plus from the ammonium. So that means if I wanted to add another alkyl group to the ammonium, I can't do it because the ammonium is not a nucleophile. So I always have to treat these with something like hydroxide to then get back the free amine. So whenever you want to make the free amine, you always have to react this with hydroxide. And getting amines in the lab, getting amines out of water is really difficult because they love to dissolve in water because they undergo this ammonium equilibrium. So if you want to get an amine out of water, if you're synthesizing one, what you have to do is load the solution up with hydroxide, and maybe you can extract the amine because the equilibrium will be more towards the free amine. But if I then wanted to say, okay, I'm going to take that amine and I'm going to add something like methyl chloride to it so I could do a second SN2 reaction, the issue is going to be that, again, I'm going to make my ammonium salt with the Cl minus as the counterient. So I'm going to make that ammonium salt as my initial product. It's only after I treat it now with more base that I'll end up with the free amine.
Where's the CH3PO come from? Or did you just add it?
I just added to it. So in other words, I can make my primary amine, then I could make a secondary amine. I could use the same alkyl group, or I could use a new alkyl group. So one of the ways to make whatever amine you want is to do a series of SN2 reactions. But the SN2 reaction always has to be followed by base in order to make the free amine. So that's a pretty straightforward method. There's another method